Hi, this is Charlie, and today we're going to go over the instructions for Lab 3, Insolations and Seasons. So we're going to look at the analemma, which is a diagram that shows the location of the subsolar point throughout the year. We're going to look at how to calculate noon sun angles, which is the angle of the sun above the horizon at noon. And we're going to look at patterns and how to read a diagram showing daily insolation values. So let's start with the analemma. Again, diagram that shows the location of the subsolar point. So there is the diagram. I grab the pointer and I'm going to go through this, but around the outside there's dates. August, September, October, November, December, January, February, March, April, May, June, July. So there's dates and months around the figure 8 of the diagram. Across the top, there's the equation of time. We're going to completely ignore how fast or slow your sundial would be. And along the left-hand side, there is the declination of the sun, which is the latitude of the subsolar point going from 23.5 north at the Tropic of Cancer to the equator to 23.5 south at the Tropic of Capricorn. So the analemma shows the position of the subsolar point. If you know the date, you know where the subsolar point is, or if you know where the subsolar point is, you know what the date is. So here's the position of the subsolar point on the June solstice, June 21st, July 21st, August 21st, September 21st, October, November, the winter or the December solstice, January, February, March 21st on the equator for the equinox, April, May, and back up to the Tropic of Cancer. So if we ignore the left-right aspects of this and just have the sun show the declination over the course of a year, you can see it goes from June, July drops a little bit, August moves a whole bunch, September moves a whole bunch. Now we're back at the equator for the September equinox, October, November. So from November to December to January, you can see it doesn't move a whole lot. From January to February moves. From February to March, we're back at the equator. March to April, we're moving. April to May, not as much. May to June, a little bit. June to July, just a little tiny bit. So over the course of the year, the rate of change of the analemma, or the rate of change of the position of the sun changes, as well as the position of the subsolar point. So if we know the latitude, 18 north, you know what the dates are. Looks like it's May 12th and August 2nd. So you just read the dates off here. They alternate black, white, little groups of 5. So you just go, well, that would be 10, that would be 11. That's May 12th. And then August 5th, 4th, 3rd, August 2nd. There you go, August 2nd. May 11th, August 2nd. Wow, I forgot I put that there. I'm glad I was right. That would have been embarrassing. Although I would just edit it and no one would know. But I'd still be embarrassing. So if you know the dates, February 25th or October 19th, those are 2 dates that the sun is at the same position. Then you just slide over and go, oh, 9 south. The subsolar point on February 25th and October 19th, it's 9 degrees south. So you can also think of it from any position, for example, from April 29 into May, into June, July. If you were at 14 degrees north, from May through June, through July, through August 15th, you would have to look north to see the sun. The rest of the year, the sun would be over the southern horizon. So April, or rather August, September, October, December, January, February, March, up to April, you'd be looking for the sun. The sun, you'd have to look south. Remember, because the subsolar point goes from 23.5 north to 23.5 south. I'll talk more about this, but if you know, if your location is in between the tropics, you can use the analemma to determine what days the sun, for example, if you were at the equator, half the year the sun would be over the northern horizon, and half the year the sun would be over the southern horizon. So if you know where you are, or you know where a given declination of the sun is, you know if you'd need to look north or south in order to see the sun. That's it for the analemma. So this next part involves a lot of math. This is calculating noon-sun angles. So today you're going to calculate the angle of the sun at noon for different locations and dates on Earth. Why do we care? High sun angles mean more intense sunlight. More energy is received at the surface if the sun is hitting the surface at a more vertical angle. Low sun angles mean less intense sunlight. So if the sun is lower on the horizon, in fact, so this is happening across the seasons. I mean, it happens every day, and so you know this. Like first thing in the morning, last thing in the evening, when the sun is low on the horizon, there's less energy hitting you from the sun as opposed to noon. If you went out and faced the sun when it's coming up, you'd feel some warmth, but it's nothing compared to if you went out at noon and faced the sun, the amount of energy that you would get. And that's because the sun gets spread out at low sun angles, so it's less intense. So over the year, the subsolar point moves between the Tropic of Cancer and the Tropic of Capricorn. So on the equinox, if you're at the equator, the sun would be directly overhead, hitting the surface at a 90-degree angle. If there was a pole standing at the equator, there would be no shadow because the sun, at noon, there would be no shadow because the sun would be directly overhead. But what if you're not exactly at the spot where the subsolar point is? Well, for every degree you are away from the subsolar point, so if you were 1 degree away from the subsolar point, the sun would be 1 degree off of vertical. If you were at 2 degrees latitude, the sun would be 2 degrees off of vertical, so the angle of the sun to the horizon would be an 88-degree angle. So for every degree you are away from the subsolar point, the sun is going to be that many degrees away from vertical. So we're going to find the angle of the sun at noon at different latitudes. There are 3 elements of information in this equation. If you know 2, you can solve or find the third. To find the noon sun angle, so that's 1, I put it in blue. To find the noon sun angle, you need to know where you are, your latitude, that's in green, and where the subsolar point is, that's in red. So if you know 2 of these, if you know where you are, and if you know where the sun is, you know what the angle is. If you know what the angle is and where you are, then you can figure out where the subsolar point is. If you know the angle and where the sun is, then you can find out your latitude. So let's go through this. We're about to find the angle of the sun at noon at different latitudes. You will use the following formula. The noon sun angle, which I'll abbreviate NSA, equals 90 degrees minus the zenith angle. The noon sun angle equals 90 degrees minus the zenith angle. The zenith angle is the number of degrees. When I say distance, that's in degrees, the number of degrees between the subsolar point and your latitude. So the zenith angle is just the number of degrees between 2 locations. In other words, the noon sun angle equals 90 degrees minus the difference between your latitude and the subsolar point. This has got a plus minus because it's really the difference between them, and I'll talk more about that. I'm going to use the ampersand to indicate that it's not like an add or subtract necessarily. It's just the difference between them. And the 90 minus your latitude plus or minus makes sense. If you were where the subsolar point is, the difference between your latitude and the subsolar point would be 0, and the noon sun angle would be 90. So if the subsolar point and your latitude are in the same hemisphere, you're going to subtract. So here we have 40 degrees north, 10 degrees north. The difference between them is going to be a 30-degree angle, so you subtract the 10 from the 40. They're in the same hemisphere, so you subtract. In fact, I would probably remember it that way. Same, subtract. Because I have a small brain and it makes it easier to remember. Equinox, equator. Summer solstice, same, subtract. So if they're in the same hemisphere, you subtract the smaller from the larger because you just want the difference between them. In this case, the difference between 40 degrees and 10 degrees is 30 degrees. Ta-da! All right. Well, if they're in the same hemisphere, subtract. If they're in different hemispheres, you add. So if we've got the difference between 30 north and 30 south, if you subtract, you're going to end up with 0. But really, you're looking, here's the equator. So that's a 30-degree angle. Here's the equator. That's another 30-degree angle. So we're going to add. They're in different hemispheres, so we're going to add 30 plus 30 equals 60 degrees. So the angle between them, if this was your location and that was the subsolar point, the zenith angle then would be 60 degrees. Again, the subsolar point and your latitude are in different hemispheres, then you add the numbers together. Let's look at crappy clip art together. All right, easy one. So the date, the September equinox, so we know where the subsolar point is. 40 degrees north. Yeah, I don't know what that means. I'll fix that later. So noon-sun angle equals 90 minus the zenith angle. The noon-sun angle equals 90 minus the zenith angle. The noon-sun angle is 90 degrees minus the difference between you and the subsolar point. So in the setup, I said you're at 40 degrees north. The subsolar point is at 0 degrees. So 90 minus 40 equals 50. So the noon-sun angle is then 50 degrees. All right. It's the December solstice. You're at 47 degrees north. So you're at 47 degrees north. The subsolar point is 23.5 south. So they're different hemispheres, so you're going to add. So 47 plus 23.5 is 70.5. So the noon-sun angle equals 90 degrees minus the zenith angle equals 19.5 degrees. So the noon-sun angle would be 19.5 degrees. All right, when I started this, I said there's 3 elements. There's the noon-sun angle, there's your latitude, and then there's the latitude of the subsolar point. If you know 2 of those, you can solve for the 3rd. So what if you know the noon-sun angle? And what if you know where the subsolar point is? And I don't know how you've done this, but you don't know where you are. How do you know? So there's 3 elements of information. If you know 2, you can find the 3rd. So there's the noon-sun angle, where you are, and the subsolar point. If you know the noon-sun angle and where you are, you can find the subsolar point. If you know the noon-sun angle and the subsolar point, you can find where you are. So the noon-sun angle is 60 degrees. So instead of trying to solve for the noon-sun angle, I'm telling you what the angle is. The noon-sun angle is 60 degrees. We are at 45 degrees north, and the angle of the sun over the horizon is 60 degrees. Okay, so the noon-sun angle equals 90 minus the zenith angle. So we know that the zenith angle equals 30 degrees, and 30 degrees is how far away from the subsolar point you are. So you're 30 degrees away from the subsolar point. Now, the people in this class who are really good at math would have realized there's 2 solutions to this. Because all I've said is you're 30 degrees away from the subsolar point. You could be 30 degrees north, or you could be 30 degrees south. So the difference between 45 north and 15 north is 30 degrees. So the subsolar point could be 15 degrees. The other solution would be 45 north, and the subsolar point, if the subsolar point was at 75 north, that would also be 30 degrees away from the subsolar point. Give me my pointer back. So the difference between 45 north and 75 north is 30 degrees. So the difference between 45 north and 75 north is 30 degrees. So that's another solution, except that the subsolar point is never farther north than 23.5 degrees. So the only solution for this problem would be the subsolar point has to be at 15 degrees north. So I'm not going to give you problems like that. That would just be way too difficult, because there's an easier way of doing this. And that is, you tell people which horizon the sun is over. So if you know which horizon the sun is over, so for example, if you're north of the equator on this day, you're going to be looking south. So The South Pole's down here. If you were north of the equator on this day, you'd be looking at the sun, and the sun would be over the southern horizon. If you were south of the equator on this day, the sun would be over your northern horizon, because you'd be looking northward in order to see the sun. Since the subsolar point is on the equator, if you're south of the equator, you have to look north. If the subsolar point's the equator and you're north of the equator, the sun is south. So, which horizon is the sun over? If you were at A, the sun is over the southern horizon. You're looking south. If you're at B, the sun is over the northern horizon because you're looking north. In fact, if you're at A, it doesn't matter the season. The highest north the sun's going to go is the Tropic of Cancer. So if you're north of the Tropic of Cancer, the sun is always over the southern horizon. Same deal. If you are south of the Tropic of Capricorn, the sun is always over the northern horizon. What if you're in the tropics, though? Well, if you're north of the tropics, the sun is always over the southern horizon. If you're south of the tropics, the sun is always over the northern horizon. But if you're in the tropics, depending on your latitude and the time of year, like if you're on the equator, 2 days a year, the sun's going to be directly overhead. Half the year, the sun is going to be over the northern horizon. And half the year, the sun's going to be over the southern horizon. So if you're in the tropics, the sun for part of the year is going to be overhead, part of the year at the northern horizon, part of the year at the southern horizon. So let's do an advanced one. The noon sun angle is 73.5 degrees over the northern horizon. So if the sun is north of us, we've got to be south of the subsolar point. So we know the latitude of the subsolar point is 23.5 because that's given. I will always have to give you 2 elements of information in order for you to solve for the third. So I want to know, where the heck are we? So here's what we know. We know that the noon sun angle is 73.5 degrees angle, is 73.5. We know that we are 16.5 degrees away from the subsolar point. 90 minus the zenith angle equals 73.5. The difference between our latitude and the subsolar point minus 90 minus that difference is 73.5. So solving for that, we get 16.5. So that tells us we're 16.5 degrees away from the subsolar point. So there's 2 solutions, right? We could either be at 40 degrees north, because that's 16.5 degrees away from the subsolar point going one way, going north, and then going south, because it's an add or subtract. So that if the subsolar point is 23.5, you could either be 16.5 degrees farther north or 16.5 degrees farther south. So those 2 options for us to be are either 40 degrees north or 7 degrees north, because both of those are getting the sun at a 73.5 degree angle because they're both 16.5 degrees away from where the subsolar point is. However, as I stated in the setup, the sun is over the northern horizon. So if we were at 40 degrees north, that's north of the subsolar point. So we'd be looking at the southern horizon. If we were at 7 degrees north, that's south of the subsolar point. So we'd be looking north. So the only answer that works is 7 degrees north, because we know the subsolar point is 23.5 degrees north. That's farther north. 23.5 is farther north than 7 north. So that's the only location that is valid for this question. Whew, that was fun. I will put up some practice problems in addition to the quiz, the pre-quiz, and the activity for this. Just some Google Sheets that you can go through and work on noon sun angles on your own to get you ready for the midterm. Good job, everybody. Good job hanging in. Maybe take a break, come back, finish this. The next topic is easier. There's no math. Treat yourself. Daily insolation. All right. Daily insolation and latitude. So this chart shows the amount of energy hitting the top of the atmosphere expressed in watts per square meter And the chart is divided by latitude along the side and by date across the top. So each entry tells you how many watts per day received at the top of the atmosphere for that latitude on that date. So time across the top and latitude across the left-hand side, going from the equator every 10 degrees up to the North Pole and then down to the South Pole. So again, the units are watts per meter per day. To put that into context, a hairdryer is about 1,500 watts. So if you were, well, let's see where we are. Oh, so it would take the energy of 3 square meters to run a hairdryer, assuming all the electricity was converted, or all the light was converted to electricity. But there's 510 watts per square meter hitting the top of the atmosphere at our latitude. So at our latitude, you'd need about 3 square meters of surface to absorb enough energy to run a hairdryer. So across the top, like I said, there's times. They're kind of weird times. It's from the data table that I think was, this was published in 1984, but I think the data might have been collected long before that. I'm not sure why they have these times, but January 13th, close enough to, beginning of the year. It's like every 3 weeks. Yeah, I think that's what I figured out. That's kind of weird. So we've got January 13th, March 21st. That's what we'll use for the March equinox. June 22nd, that's what we're going to use for the June solstice. September 23rd, that's the date that we will use for the September equinox. And then December 22nd is the date that we'll use for the December solstice. So across the side, we've got, 90 degrees, we've got 40 degrees. And then if you find the date and the latitude, so let's go on the June solstice, and at the equator, the amount of energy received at the top of the atmosphere over the equator on the June solstice is 407 watts per square meter per day. So the big important thing is what we're looking at is comparisons in energy received at the surface of Earth as a function of latitude. So these graphs are looking at one latitude. So now running across the bottom is time, but we're only seeing the curve of energy for one latitude. So at the North Pole, they have no energy. March 21st on the equinox, the sun comes up, it's up for 6 months, it sets, and then it's down for 6 months. So the two things that I want you to be aware of are the closer to the equator. So here's the line for the equator, and it's pretty much a flat line. The closer you are to the equator, the less seasonality there is. Every day is 12 hours, and they're getting just over 440, 450, 460, 460, 450, 430, 414, 407, 412, 420, 440, 450, 450, 450, 440, 430. So between 407 and 460 watts. So just over a 10% variation over the course of a year between the most and the least, as opposed to here at the poles when it goes from 555 watts down to 0. So the farther away from the equator, the greater the difference between summertime with 555 watts and wintertime, 0 watts. Same thing at the South Pole. They have the same pattern, except they actually get more energy, 592 watts, because Earth is slightly closer to the sun in January than it is in July and June, which is nice if you live in the Northern Hemisphere. So they also have 6 months with no energy, and then an enormous amount for those 6 months the sun is up, because if you're actually at the North Pole, you've got 6 months of pretty much continuous daylight. Like the sun does not set. It's just up 24 hours a day, month after month after month. So the sun's hitting the surface at a really slanting angle, but because we're getting 24 hours, you can rack up almost 600 watts of power per day, which is the most from any latitude for any period of time. It's weird that at the North Pole, at the South Pole, because Earth is slightly closer and they get 24 hours of light, they're racking up almost 600 watts of energy. And where we are, New York, Rumsey, Paris, Milan, Sacramento, all the world's capitals are about 40 degrees north. So at 40 degrees north, there is almost a threefold increase in energy, like 163 watts per day on the winter solstice, and on the summer solstice, yeah, almost three times as much energy, 510 watts compared with 163 watts. So that's the other aspect, is if you're by the equator every day, you're getting close to the same amount of energy. And as you move away from the equator, the difference between summer, 500 watts, and winter, no energy, gets bigger and bigger and bigger. So this is a plot that I did just for kicks and giggles, going from the equator. So that's 0, 10, 20 degrees, 30, 40, 50, 60, and 90. I didn't do 70 or 80 degrees, but you can see at 90 degrees, there's no energy from the sun up until March 21st. And then boom, lots and lots of energy. And then a mirror drops off down to nothing. Whereas at the equator, you can see it's pretty consistent, running between about 400 and just over 450 watts per day. And then finally for us, at 40 degrees north, let's see, which one are we? I think we're this one. Yeah, we're that one, 40 degrees north. So you can see at 40 degrees north, we're getting fewer than 200 watts in the winter, and closer to 500 watts in the summer. So over 2 to 3 times as much energy in the summer as in the winter at 40 degrees north. And then this is showing, let's see, we've got the South Pole, nothing from March, April, June, August, September solstice, or September equinox rather, the sun pops back up and they've got 6 months of sun. So this is comparing, again, the equator with 40 degrees north with 90 degrees north. So you can see the difference between the equator, where every day you're probably getting about the same amount of energy, with 40 degrees north. All right, that's it for daily insolation and latitude, and that's it for the how-to video for Lab 3 Insolation and Seasons. I wish you good luck on the lab. If you have any questions at all, I would love to talk about it with you. Please show up at Zoom, send me a text, send me an email, give me a phone call, whatever works for you. Good luck.